Awesome. All right, hi everybody. It's great to be here. My name is Craig Taylor. I'm a PhD student at University of New Mexico, and that is the group that leads the long wavelength array collaboration. It's a low frequency telescope collaboration with several other institutions, and I'm hoping to give kind of a broad update on some of our activities recently, as well as a little bit of some personal things that I've been working on as part of my PhD. And I'm hoping to finish that up this year. So this is a great talk to give you guys because that sort of has a little bit of something for everyone, hopefully. So briefly, I'll introduce the long wavelength array. So this is a dipole interferometer array. We have 256 of these antennas that look kind of like this guy, a little animation I made. And this is our Sevilleta station. It's about 45 minutes south of Albuquerque. It's half hour north of here. These telescopes operate between 10 to 88 megahertz. It kind of depends on who you ask. Maybe you can push that down to something like 3 megahertz for things like ionosphere science. And some of our collaborators at Caltech do some other kind of strange things with frequency because they have a little bit more instrumentation. But nominally, when you're observing for targeted runs and in all sky mode, you get about 20 megahertz of bandwidth to work with, and that's within the entire range. So you can kind of slide that around wherever you need for your given science. Like I alluded to, these stations work in kind of two primary modes. The first is using steerable beams, much like any other radio telescope with BLA. But we also have access to an off-sky imaging mode, right? Because we have these dipole antennas, and they have a very wide field of view, and so we can just kind of use their all-sky beam in the same way that we use the directed beams, but with a little bit different settings. And so that kind of enables us to do a lot of variety of science all at the same time, because these two systems are commensal, meaning that the all-sky imager is basically running all the time. You can go to the LWA website and you can look at the sky right now if you want to from our telescopes. There's little drop downs. You can even change the frequency around. You can change the stations. It's really cool. And then at the same time, we can do kind of directed science experiments with these type beams and look at sources like AGN or pulsars or what have you. Now, it's kind of cool to show that we actually have flavors of LWA stations now. So these two stations here on the top row are kind of the first two babies of the LWA project. LWA 1 here, you'll notice, is at the VLA. Co-located a little bit behind the antenna barn. Sevilleta Station is on the Sevilleta National Wildlife Refuge, which I said is a little bit north of here. My PhD has been worked to develop what we call the LWA North Arm, which if you drive all the way down to the north arm of the VLA, all the way to the last antenna, we're kind of sitting right next to there. This is a little bit more of a compact array, you can see. So I put the circle on all the plots to show kind of the aperture size for the standard LWA station. They give you a reference point for the other types. So the LWA North Arm is 64 antennas as opposed to 256. So we've got a little bit more of a compact configuration, but it's not strictly a 1/4. The total collecting area here is closer to like 80 meters as opposed to 50. So we're kind of somewhere in the middle between a quarter-size station. And then LWA Ovro is at the Owens Valley Radio Observatory, which is in Eastern California. You can see that there's the core here with that black circle around it, but then they've added all these other long baseline antennas out to give them high-resolution imaging and do other cool things like cosmic ray searches using showers. So these are kind of the four flavors that the LWA is operating on right now, and this continues to develop. The LWA system is kind of designed to be customizable to the budget of a different project. And so this demonstrator array here down at the north arm of the VLA is kind of to show that you can get a lot of power out of even smaller stations. So here's kind of a little bit of a zoom in. On the right, I've shown the layout concept for the north arm station. It's actually the Sevilleta station, but just sampled using an optimizing function so that we can have 64 antennas, but have them better distributed across the area. And also, you can see these kind of rigid lines dictating the trenches that we use for cabling. We use kind of a nearest neighbor algorithm to reduce the amount of cable that we had to use. And so we also implemented kind of an interesting trenching strategy for this station. So this is a quarter size, 64 antennas instead of 256, with the same configuration modes as all the other stations. Actually, maybe even more. We've got a little bit newer electronics in the North Arm station, so we can actually save that full kind of 80 megahertz of bandwidth at a time. The other stations are kind of closer restricted to the 20 megahertz that I talked about earlier. But one of the main goals was to incorporate more readily available hardware. Things are expensive now, especially electronics. And so having to custom build all of your back end or front end electronics for these kinds of stations can be prohibitively expensive. So if we can leverage the commercial market for things like field programmable gate arrays or cabling or other electronics, then we can lower the cost of these stations and hopefully distribute them to other institutions or be able to build more of them ourselves. I'm going to give you now a quick rundown of the construction of this particular station because it is, like I mentioned, the bulk of my thesis. And so here's where we are. So this is the BLA pad all the way at the end of the North Arm, and we're about a kilometer west of that. You can see that we are stealing our power and optics from the BLA. Thank you very much for that. We appreciate it. And it's just accessible by county access roads. The first thing that we did is survey the site. So previously there was instruments from the LWA, which is sort of the before LWA1 was built. That was where they were testing antennas. There was a low phasm station out there as well. I think for a time there was also a T-Light station, which is an ionosphere project. So the first thing that we had to do was survey the site. And then the next thing we do, you can see some surveying here, is we got to pump iron. So these are the masts of those LWA antennas. We got to use a jackhammer and pound the spikes that they sit in all the way into the ground, and do that for all the antennas. And so after we survey, we slammed in the antennas. We used a commercial telecom shelter. Previous stations used custom-built shipping containers that had augmentations to the RF shielding. But for this, in order to reduce costs, and as a demonstrator that the shielding requirements are probably lower for an LWA station than is required at the other stations, or is used at the other stations, rather. And so we modified the telecom shelter. We cut out all of the paint that they put in the door jamb so that it was sealed properly, and added in all kinds of stuff. And then the BLA staff kindly used their crane to drop it onto our concrete pad there at the North Arm. Here we had to do, here's me on our trencher that we used to trench the site, and some of my friends and other students out here. This was a very student-led project, and so most of the time it was me walking down the hall to people's offices and knocking and say, hey, you want to drive 3 hours out to the BLA and work on this in the summertime with me? So we had a lot of fun doing this kind of as maybe a student-led project. Here you can see more students constructing the antennas. So once we had all the antennas masts installed and the cabling for them, we can put all the rest of the bells and whistles on our antennas. We also were able to borrow some students from collaborators at Hillsdale College, which is in Michigan, which is kind of cool. And we wrote some instructions for how to put these things together. So if any of you guys want to build an entire LWA station and you've got $500,000 burning a hole in your pocket, I got all the documentation you'll need to build one for yourself. So this is kind of a timeline overview. This is myself, Logan Cordonier, and Evan Sheldall, other graduate students. This is the last day that we were building antennas. Thankfully, we completed the station. And so all in all, it took about a year and a half from tearing everything down that used to be there, surveying the site, and then building it all back from the ground up. So what do we get out of it, right? So on the right is the all-sky image that you'll see on the website for LWA Sevilleta, and on the right is the North Arm image. So you can see there's some effects in the sensitivity and angular resolution. That's pretty obvious, and given the reduced size and the reduced aperture. And we also have a little bit we have a little bit more sensitivity on the horizons to RFI because of the location. some of the power lines out close to the end of the VLA there are particularly loud and particularly loud at low frequencies. So we get a lot more RFI at the North Arm station than others, but that's just a project for us to work on the power company with. So quickly, we'll move out of kind of the instrumentation and construction, and we'll go into a little bit of data, which maybe you guys are a little bit more interested in. And if you have questions, just stop. It's a little dark in here, so I don't see you. Just sort of, frowning person, wave your arms at me. So we did a couple of observations in order to kind of verify that the telescope was ready to go. This is a step that kind of was woven in at the other stations into their kind of launch. But for this, we wanted to take a little bit of time to make these test observations and characterize this kind of reduced telescope. So the first test that we implemented uses the steerable beams where we look at we use two different antennas at different places in the array, and we basically just look straight up with single antennas. We make sure that as the sky drifts over, that we see the galactic plane rise, and we see it set at the correct times, and we see it the same at both antennas. So that's what you'll see here. So we selected two central tunings, one at about 40 megahertz and one at about 74 megahertz. And then we simulated what the sky should look like with a single antenna for an entire day. You'll see that in these yellow and green dots that are overlaid on these curves. Now, the blue and red data is the XX and YY polarization from each of the antennas. And so you can see that we're doing a pretty good job of following along with what we expect. And we have pretty good models of our antennas, and we have a fairly robust model of the sky at our frequencies. And so it's pretty easy to kind of put these two things together to really test how well we're seeing the sky. There's a couple of regions here in gray where I've clipped out RFI from the power lines. It sort of dominates our spectrum across the board generally, and so I kind of just snipped those out. There was also a little bit of solar activity here in the higher frequencies that was detected, so that's why we also have a little bit of a deviation there. But all in all, this is a pretty good fit to what we estimate the data to be, which is great. Another test, I'm gonna go back to this slide really quick. Another test that we can do is we can take two beams at the same time, right? So I mentioned that the LWA stations have commensal systems with the all-sky imaging and the beam forming. What I forgot to mention is that each station is equipped with 4 beams. So we've got 4 digital backend pipelines that can run all at the same time. So we could run those 2 antennas at the same time, but we can also use the entire array and look at 2 different places at the same time. And so we can do that, and we can also switch back and forth between the sources. So for example, one of our tests, we looked at Cassiopeia A, which is very bright at the low frequency in radio. And then we look over at the North Celestial Pole, which is essentially dark skies for us at these frequencies. And then we can see how quickly can we flip-flop between those two using these software beams. Now, we assume that's very quickly because this is kind of a software-defined system, so it's on more computer time, and we're more restricted by things like our FFT window. But that's what I'm showing on this plot here. So starting at 2 seconds and then geometrically decreasing the amount of time per pointing, we switch between Cassiopeia A and the North Celestial Pole. And we reduce that by a factor of 2 every time, or every 2 swaps, all the way down to 62.5 milliseconds. Now, I don't think that there's too many projects that are going to need to switch targets in 62.5 milliseconds, but it's really cool to see that even from 1 second time resolution all the way down to our lowest, we can pretty much get on source within 62.5 milliseconds every time, which is really great. That opens up sort of more interesting observing strategies. For example, one example would be in optical, they do something called speckle imaging to kind of characterize their atmospheric environment that they're looking through. So in radio, we might be able to do that by taking these 4 beams and quickly looking across the sky at a variety of sources to characterize the lens that we're looking through in the ionosphere, and then make corrections to that. So there are practical applications for some of these kind of more obscure tests. Okay, Great. From here, I'm going to move into some actual science that we did, some kind of test case science to include in our publication on the kind of construction of this station as a proof of concept that we can do cool stuff. So one of the primary focuses for LWA recently over the last decade has been ionospheric research, particularly in sporadic E. So in collaboration with the Air Force Research Lab, they are very interested in the E layer of the ionosphere. So during the day, it gets ionized and becomes much larger and more active. And we can get these things called sporadic E, which are these thin overdensities in the ionosphere that can reflect basically just ambient radio that comes from anybody. So it could come from, people that are using ham radios, or it could come from things like a city's power grid just sort of leaking out of the transformers. And at sufficiently low angles, this will reflect into radio receivers. This should affect pretty much all radio equipment, but at low frequencies, we're particularly sensitive to that. And so what we would like to do is be able to track these kind of thin, dense structures in the ionosphere in order to be able to understand how they evolve and their dynamics, and maybe some statistics on how they interfere with our telescope. And so now that we have kind of 3 stations that are pretty close together in LWA1, Sevier, and North Arm, we can do proper triangulation of these sources using tomography and locate them. So in each of these plots here, you'll see all sky images from the 3 stations. And on the right, I've kind of pointed an arrow to a sporadic E. Generally, they don't look like point sources like this. They're much more broadly defined. They have large azimuthal angles, and they move and evolve very slowly with time. Timescales of minutes to hours. So they're very bright, they're slow moving, they're constrained to the horizon because of our sensitivity constraints. And because of that, they're pretty easy to track. And so we can go through our archival data and triangulate these over a map of the US. So on this plot back here, I've put a little orientation here because it's to the sky, so it's mirrored. But you can see that we're able to kind of put this fairly compact source on the horizon somewhere over central Arizona, which is cool. There are other things that we can do. We can put something called a digisonde, a sounder in Arizona, and that will shoot a laser up and down, and it measures the kind of the strata of the ionosphere. And so using that, we can also track sporadic E's, because as they drift directly overhead of those sounders, it inserts a highly reflective lens at low frequencies. Usually those digisondes operate below 10 megahertz. And so the ionosphere will be very reflective at those frequencies. And so we've done that. There's one that's in Fort Stockton in Texas, and we're supposed to put a few more in around New Mexico and Colorado, and maybe in Arizona too. This is a collaboration with the Air Force, and so they have a little bit more access to properties and things to drop these sensors down. And so that's why there's one in Fort Stockton right now that we're using. Looking to the future, very briefly, I want to give you the map view that is even more zoomed out of this to show you how this capability could be improved in the future, and to show you kind of the outlook for our development. So here is another map with the 3 stations that I've primarily been talking about here in New Mexico. LWA1 and Sevier in red as 256 element stations. LWA North Arm in blue is a mini station, or what we're calling a swarm station. And then the Owens Valley Radio Observatory LWA station is kind of that super station that I showed earlier. But there is also 2 more on here. There is LWA Comanche Springs. At the Comanche Springs, what is it? It's like the 4 Corner Science Consortium or something like that. There's an amateur astronomy facility that's in North Texas, and that we've collaborated with to put in another one of these small stations with Texas Tech And then we also have LWA MC, LWA Meteor Crater. So this is a collaboration with Arizona State to put one of these 64 element stations at the Meteor Crater National Monument. So pretty soon, and hopefully the next year or two, we'll have a fairly large, low frequency, essentially east-west array that we can do some kind of interesting interferometry observations with. Currently, the only active stations are these three here in New Mexico and Owens Valley. So most of the work that we've been doing to kind of push into interferometry has been locally in New Mexico. This kind of acute baseline out to California is difficult to manage, and they operate in a different way in some ways than we operate the stations here in New Mexico. So there are a little bit of operational challenges in setting up those observations too. But I'll have a highlight of that here in a little bit. So that's kind of the single station testing, how you build an LWA station, things you can do with it on its own. But what we're really interested in is the LWA as an interferometer, right? That's kind of how I introduced my talk. And so what I've been working on this year is the first calibrator survey for the LWA interferometer using 3 stations. And then we've also done a little bit of testing beyond 3 stations. And so I'll get into that as well as kind of a show and tell of some of the things that we're just starting to get into. So this is a diagram of a basic 2-element interferometer. It is sensitive to, we're measuring the brightness distribution of the sky and implementing delays that we know in order to combine these signals that we're measuring at individual antennas. But we rely, the kind of theoretical example that I have here on the right that you'll find in a radio astronomy textbook is motivated by a lot of assumptions, particularly things like light propagating in a vacuum to our antennas, finite bandwidth constraints. Identical hardware is a big thing for LWA. The first station was built in 2012, and it still has a custom backend that was built by JPL at the time, whereas the North Arm station uses mostly off-the-shelf electronics that are kind of reconfigured. And so we've got a lot of spread in hardware that also makes it difficult to combine these things. And that is only a few of the constraints that limit your use of interferometers. The nice thing is single stations are essentially an interferometer array. And so a lot of these things we've already worked out or are known. For example, the delays to the individual antennas, pretty much fairly accurately known. But there are also other things that we can't control, such as the ionosphere, as I've alluded to, which is a dispersive electromagnetic lens. It is increasingly effective at lower frequency because of this inverse proportionality. And so we get hit much harder than the VLA does, for example. And it introduces these rapidly varying terms in our phase information that we need to solve out in order to make these observations. So to do that, we need calibrators that we can look at for every observation. In order to make observations of really cool things also, such as the Jovian dam emission or stellar flares or solar flares, or also more kind of hot topics like pulsars and pulsar timing arrays. We need to have good calibrators in order to make sensitive observations. So what kind of do we classify as a good calibrator? It's a little bit different according to what telescope you're using and what frequency range. And for us at low frequency, we're much more limited than something like the VLA. So we need them to be bright at low frequency, but we also need them to be compact. We need the emission region to be small enough that when we go to these low frequencies, it doesn't blow up in angular size. We need accurate positions, which is not so bad because we have the VLA, which is much beefier and much better at pointing and looking at these compact sources. And so they can supply us with the accurate positions that we need. But a problem that we have, the VLA does, is we can't tilt our antennas. Our antennas all sit and they all look straight up. And so our sky is subject to a sine projection or an inverse cosine projection, meaning that we basically don't observe anything that's below 30 degrees in elevation. if you get down anywhere lower than that, then you're really smearing out your signal and the beam size, and so we kind of want to stay away from that, particularly because these things are hard to find. So I've kind of highlighted one of our calibrators, 3C380. This is from the VLSSR survey, the Very Low Frequency Sky survey. But this is in log space, right? So in linear space, it looks like this. This is what a good calibrator that we're looking for looks like. It's very bright. There's nothing really around it to confuse our signals. But luckily for us, at low frequencies, there aren't too many of these. So it's more of finding ones that we can actually detect as opposed to sorting through crowded fields. Another problem that we have to deal with is that we only have 3 antennas. And so for a given 10-minute scan, on the right-hand side, this is our sampling of the UV plane looking at 3C147. So I don't know about you, but this is not awesome sampling of the parameter space. We don't get a whole lot of sensitivity or resolution in just one 10-minute scan. And so we have to rely on Earth rotation synthesis. Very historical for things like east-west arrays, like we kind of have set up here in New Mexico. And so for a given observation, we'll actually do, we kind of stick to 8 hours. We need to have we have a lot of time to observe so that we can fill out this plane as I've shown kind of this animation. Each one of these bundles is one 10-minute run that we add on. So over the day, as we kind of link between 3C147 and our target source, we can fill out this plane. And what this actually looks like practically is over here on the right. So each, if you look really closely on here, you'll see a bunch of lines kind of running up these. So one of these tracks is a single one of these lines. We got 40 frequencies that we use for these observations, and so we can kind of leverage our ability to break up our frequency into chunks in order to better sample the UV plane. And so these are frequencies. What frequencies? Yeah.
Is it a closely spaced? So
yeah. So for us, we choose our frequencies more on the sensitivity constraints. So for this survey, I chose tunings of 55 and 74 megahertz, which is basically just the top most contiguous section of our frequency band. So it's about 40 megahertz, and then we chop it up into about 1 megahertz chunks. And most of that is just for imaging. So to give us better coverage of the UV plane. We haven't really got outside of strictly just imaging the sources and looking for more interesting things within the signals. But thank you for the question. Yeah, I should have mentioned that. So that's why you'll see these plots are centered at 65 megahertz. It's kind of the middle of our observing window.
Question.
Yeah.
Can you explain what the UV plane is?
Yeah, great. So so when we use interferometers, we are sampling what's called the visibility function. So the brightness distribution of the sky in Fourier space is what we call the visibility function. And so when we observe using these interferometers, we are sampling that function. And that function is a spatial function, right? So that's why these plots over here are, hey now, bring that back. That's why these plots here are in kind of U and V coordinates. So U and V coordinates is the coordinate space where the visibility function lives in. And this is, sorry.
Oh, okay. Yeah.
Yeah. Yeah, so that's where we're kind of making these measurements. We're sampling that function that's on the sky.
Oh, okay.
And so this is sort of a visual representation of our sampling of the brightness distribution of the sky in the select region that we're viewing. So for these interferometry observations, our beam size is mostly subject to the North Arm telescope. It is a little bit smaller, so it has a larger beam size than the other 2 stations. So for these observations, our beam size estimate is like, the full beam is somewhere between 1 and 3 degrees in size. So very big, very big. But the nice thing is there's not very much stuff to look at inside the beam at these low frequencies. So that gives us a little bit of an advantage. Thanks for the question, Jason. Okay, so what are we looking at? So I culled most of the sources for this survey from two things. Primarily one from the VLA calibrator manual. They've been doing it a lot longer than I have. So I'm keen to use their best calibrators first. But then we also sampled a section of sources from the 4-meter survey that has been going on for the last couple of years to get the rest of the sources. We chose everything that's above 40 Janskis and everything that's above 10 degrees declination. That sort of keeps us in a regime where we can observe sources from 30 degrees elevation on rise to 30 degrees elevation as it sets in about 8 hours. And it gives us okay coverage in right ascension and declination. I would like to see this filled out much better, because ideally for these kinds of observations, we want our calibrators to be within a beam size away from the target source, just so that we're looking through that same atmospheric lens. But at low frequencies, we kind of get what we get. So in black, you'll see sources that we've already observed for our campaign. And in red, you'll see sources that we have not yet observed in our campaign. Currently, the campaign is finished. I'll get to a little bit why there are some sources that are still unobserved at the end of the talk. But effectively, this is kind of our sample. We would like to have more, but this is kind of the best we could do with our equipment.
So why wouldn't you use Cassiopeia?
Great question. Great question.
So, I mean, it's bright and you know what it is.
Yeah.
Wouldn't that be a great calibrator?
Yeah, right. So this survey specifically excludes 4 sources, which are the A-team sources. So Cygnus A, Cassiopeia A, Virgo A, and Tau A. All of those sources are going to be resolved in our beam, and so we can't use them as calibrators because they're so bright and they have such large angular scales because of that it just fills up our beam, and it's not really useful because you can't identify the fringe signal because it's sort of just, you're kind of blasted basically. So we kind of actually steer away from those sources and we give them like a big cushion. Similarly for things like all sky studies, we kind of stay away from those if we're looking for fainter sources. But on the other hand, things like Cassiopeia A are great for calibrating the all sky images because they are super bright, and so they have well characterized flux densities at a variety of frequencies. And so we generally use things like the A-team sources for calibrating the all sky images and fitting their brightness as a function of altitude. Yeah, thanks for the question. So all of these black dots, what do they look like in radio images? Ta-da! These are our amazing photographs. This is our zoo of sources. You can see that some of them are much more compact and well-behaved than others. This is a little bit to do with altitude. Some of these sources that are a bit more smeared out don't get as high in the sky as others. But as a reference, earlier I showed an image of 3C380 down here from the VLSSR. And this is the window that we're viewing from that image before. So we're really just looking at the small region around the sources and trying to really understand the properties of them and how well we can use them to calibrate our telescope. And so things like these guys up here are going to be much better calibrators than sources like these down in the corner. But at least for us, we can get solutions for some of these fainter and more low elevation sources.
What's the angular resolution?
The angular resolution, it's like the scale is kind of hard to see. So down here in the left-hand corner is the resolution beam, and so it's like 10 arc seconds, 20 arc seconds. It kind of depends. We get a little bit better with including the Owens Valley, which I'll show here on the next slide, and then much better incorporating the VLA. But the VLA has a little bit of other quirks as well. Okay, great. So I mentioned that we've tried observing with Owens Valley. There are a couple of operational issues with that. One is that these observations, each station records about 2 terabytes of data for 1 8-hour run. And so to copy 2 terabytes of data from Owens Valley to the University of New Mexico, it takes like 7 days because they have a crappy internet connection. And so that is kind of like one delay. The other delay is that our correlator works at about 50% observing efficiency. So an 8-hour run takes about 16 hours to correlate. So we can add that on to that. And for me, for some reason, Owens Valley doesn't really care to upkeep the voltage beam that we use for these observations. So they use power beams for most of their observing. And so typically that means that when my observations come up, the power beam or the voltage beam, excuse me, is not configured most of the time. So I've got to get on there a couple hours before and fight with it to configure it. And so there's a lot of operational challenges that we're hoping to remedy here in the near future as we get better at making these observations. So here is an image from one of those observations. This is 3C147 again. So I'll flip back to this slide. And it's this guy up here. So you can see some of our geometry is affecting the shape of this, but the beam size is much smaller than on the previous plots. The 1,000 kilometer baseline converts to about 1 arcsecond resolution at 65 megahertz. That's a really rough conversion, but we're hoping that with better observations primarily, and that means better calibration for the Owens Valley telescope, and more regular observations, we can kind of clean these images up. Because we've only really had about 2 successful runs in 6 months using Owens Valley, despite about 8 attempts. So we're really limited by operations in that front. Quickly, the limitations I've kind of described as we've kind of gone along this journey. But the main one is Earth rotation synthesis. We just need more antennas. We need more telescopes. We need them distributed in a more uniform way as opposed to in line, which unfortunately our newer developments this year are continuing our kind of east-west stretch, but hopefully with more collaborations we can add more. Proper amplitude calibration requires 4 stations. So right now, currently, we're using a solved set of static amplitude coefficients to kind of equalize the power at all of our stations. But if we could more regularly use the Owens Valley, then we can optimize the solving for that. And each observation can have its own unique set of solutions that equalize the amplitudes. And then computation time. I guess that we're at 50% efficiency with our correlator. And so one of the big pushes is to acquire grant funding to upgrade that and build a sort of an LWA computing facility that's standalone and is much beefier than the one that we have right now. We've got some proposals submitted for that, and hopefully when we construct these stations here in 2025 and 2026, that'll kind of increase the funding impetus to kind of help us out with that. Low frequency astronomy is one of the priorities in the decadal survey for the next 10 years outlook in astronomy. So crossing our fingers that means that they'll give us some more money. And then another cool thing that we can do, this is kind of an aside since we're here at the VLA, is there's a 4-band system from 54 to 86 megahertz, 4-meter band system on each VLA antenna. This is the feed horn, and it uses these J-pole antennas that you can see here kind of bracketing in that feed. So that will give us a lot of power. It gives us a lot more baselines for one. We don't really add that much to the VLA in this configuration. We're more taking as much as they can give us in terms of sensitivity. And so we get a lot better resolution with having a lot more baselines, and we get a lot more sensitivity by having all the extra antennas. I think roughly 1 VLA antenna sensitivity converts to 1 full-size LWA station at this frequency. And so we're adding, at best, 27 extra antennas to this LWA interferometer. The problem is that the voltage regulators inside of the VLA antennas, inside the antenna itself, likes to emit at between 54 and 86 megahertz, and it's very loud. And so when we look at pretty much anything, all of the VLA antennas at 74 megahertz, they all see each other. And because they're seeing other antennas, the emission, because they can see other antennas and they can also see themselves emitting, this RFI actually correlates. And so it becomes a really corruptive signal in our observing. The nice thing is that the VLA is planning to install filters this year to kind of remedy that. There is one test, filter that's already installed on antenna 10. But now that we're in deconfiguration, the engineers at the VLA are going to cycle through adding in the rest of the filters, so that hopefully in 2026, when we go back out to A configuration, we can do some more testing using this 4-band system. I guess that is something I should mention. We only really want to use this in A configuration because we want the longest baselines, for one, and two, in any of the tighter configurations, it just ramps up the RFI even more. So we sort of have to wait our turn in order to get these observations to come back around.
4 minutes.
Great, thanks.
Yep.
But here is a few images from our test observations. This is the UV coverage of the VLA plus the LWA. Our contribution is these triangles out here, and then a little bit of the stuff here in the center. Most of the rest of this is just all VLA worked in for us. But with these long baselines, we can maybe get a little bit better sensitivity and a little bit tighter angular resolution. So here on the right is an observation of 3C295. You can see the beam size down here is also, it's kind of on the same scale as the LWA observations, but that may be constrained due to the kind of crappy data that we get. There's a lot of flagging that's involved here. But the nice thing is that it's very hard to see, but this is the field that we're looking at here in the middle plot. But there's also a field source up here and another field source down here that we were able to detect using the ELWA mode that we weren't able to see using just 3 LWA stations. So we're hoping that once the filters get installed and we get back onto A configuration, we can do some pretty cool observing of these fields and see some of these fainter background sources that most of the time fall out in our LWA observations. There's a couple of sources that are closer to like 50 Janskis that have some neighbors that are in maybe the 10 or 20 Jansky range. Sometimes we can pick out, but usually we're only looking at the dominant source in the field. So with that, I'm just going to wrap up and leave a summary up here. We've just completed this survey. Unfortunately, as I said earlier, we completed the survey because LWA1 has actually failed. This is recent news. About 2 weeks ago, the digital processor, after a power outage, died finally. We've sort of been dragging it along over the last 6 months, bringing it back to life every time it tries to die on us. But we officially put the nail in the casket about 2 weeks ago for LWA1. The nice thing is we already had plans in place to redo the entire back end of both LWA1 and LWA Sevieta starting this year. So Sevieta will start its upgrades in hopefully April. We are currently testing the analog receiver boards in the lab at UNM. And then LWA1 is going to be second in line after we upgrade Sevieta, mostly because it's easier to drive 45 minutes and test everything than it is to drive 2.5 hours. So we're doing our close friend first and then learn all the things we need to with that before we work on LWA1. So I'm optimistic that after this year, that we'll produce really cool interferometry with more stations. And the outlook looks good for the LWA. So thank you for your time. I appreciate you guys hosting me here. And if you have any questions, I'd be happy to answer.
But what accounts for the elongation of some of the images versus the point, the round versus the elongated images in one side?
So
like there.
Yeah, so like 3C161, for example, compared to maybe 196 above it. most of that is due to the maximum altitude of the source that we're observing. So our beam, because we can't tilt the antennas, our beam is subject to an inverse cosine law. So as we look lower in altitude, it sort of stretches out. And so the angle of this kind of elongation is a function of the geometry of the array and the location of the source that we're looking at. And then well, kind of mixed into that is the beam, right? So you can see that on some of these sources, 196 is a much higher declination source than 161. And so you can see here the beam is also tighter as opposed to down here where it's kind of stretched out. That sort of encodes that kind of information.
Why don't we reverse it back and fix that thing?
Why don't we, like turn and it's sort of in the other direction?
Why don't you just calculate, because you know where you are relative to the sky here, right? So factor that back in and then take the elongated and make it fix it.
Yeah, but I mean, this structure isn't encoded in the sensitivity of the beam shape, and so we're subject to the properties of the beam as it's phased to a different altitude. So we would only be able to do that with more antennas, so that we can have better coverage of the UV plane. That would help kind of like round it out, and then just more observations. We don't stack. It's not strictly trivial to try to like reconstruct that in this context.
Theoretically, if you had a more swarm or even a big one, hypothetically, we might have 500,000 laying around.
Sure.
In San Diego, out in the desert, 50, 60 miles east. Would that be something that would be, I realize it's one more east-west.
Yeah.
But would that be useful to you?
Yeah, I mean, I think that more antennas is always better, just because more collecting area. We only have a couple of antennas, so we have to observe for so long anyways. But for an east-west array, we're already observing for a long time. So, adding more kind of along our plane just kind of makes us a little bit better. What would make us a lot better is something like a telescope in Colorado or in like North Mexico or something like that. Just give us a little bit, we can fill out our UV plane quicker that way and make better images.
So I hate to cut it short, if we have, but we have our next online participant is supposed to start at 10:30. But if you have more questions for Craig,
Come find
definitely catch him off to the
Yeah.
side.
I'll be here. all
Thank
day.
you, man.
Yeah, appreciate it.
it.
You're always.